Hello everyone, welcome to the second session of Deep Test. We will start with a keynote with not only one but two speakers, and then we will have two paper presentation, and we will end like the previous session with the Q&A. I invite everybody to add your questions in the chat so we can read them and forward them to the speakers. But let's start to introduce the keynote speakers today. We have Natalia Gusevska, that is a research engineer at Facebook. It's a software engineer. She had a master's degree at the École Polytechnique de Lausanne in Switzerland. That is actually the Switzerland from we are talking right now. And we have we are presenting these speakers that are from industry but have a deep relationship with the academia. Natalia had a great prize in interdisciplinary team. She won a gold medal in 2017 at EGEM, and then since 2019 she started working at Facebook in the group of Mark. Well, it's really difficult to introduce Mark Harman. He's actually a legend. He's the co-founder of the search-based software engineering topic, and we owe a lot to him because he has inspired us software testers. And I invite you to read his papers, his tutorial about search-based software engineering. But recently he started also to, despite still working part-time for the UCL, now he is now working as a research scientist at Facebook, and they will present now for our workshop, the full version, the best version of what they already presented at the SAPE session at ICSI. That is about digital twin of Facebook that includes machine learning components. Please, the stage is yours.
Thank you very much, Vincenzo. So I'm just going to share my screen now, and in so doing, you should be able to see my slides.
Yes, we can see.
Right, great. Thanks very much. So thanks very much for that kind invitation. So we have an hour together, and in this hour, we split it into 3 equal parts. So I'm going to give the first part of the keynote talk today, setting a little bit of the context about this digital twin that Vincenzo was talking about. It's a cyber digital twin that we've built of Facebook's dub platform, and so we call it dub or WW because it's a cut down version of our dub platform. Then 20 minutes in, I should hand over to Natalia, who's going to tell you in much more detail about how we test this platform, and then we'll have plenty of time at the end for questions and discussion. So I really encourage you to put as many questions as you can as we're going, and then when we get to the end, we'll have plenty of time to discuss those. So I should mention that although it's Natalia and I who are giving the keynote today, this is actually the work of the whole team in London. There are at least 10 engineers working together with us on this project, and this is joint work from the whole team. So in today's talk, we're going to cover the Oracle problem and the way it's particularly pernicious for simulation, and how we use metamorphic and regression testing to tackle these problems at Facebook, the MIA system that we've built at Facebook. MIA stands for the Metamorphic Interaction Automaton. It's a metamorphic testing system around our dub simulation system. And we'll talk in particular about how we use different versions of the cyber digital twin to tackle problems of flakiness and scale, particularly using offline modes. And Natalia will go into much more detail about that, her part of the talk. So you might start by thinking, well, why should I care about simulation? You may think that simulation is just one very narrow application area in computer science. And so why is it so important? But I'd like to encourage you to think about how simulation perhaps has crept up on us as a really powerful and important application area for software engineering. In fact, I'm speaking to you now from London, where we've just come out of lockdown. for COVID, and those lockdowns were actually decisions made by government entirely informed by simulation. As we think about deploying autonomous vehicles, as we were discussing just before in the backstage, we're talking about at SBST how autonomous vehicles require simulation for their deployment. Also, the very future of our planet depends on simulation. If you think about the effects of climate change and how we use simulation for that. So really throughout economics, through government, through decision making, organizations are increasingly turning to simulation. And therefore, I feel that this is an area that needs much more attention from the software engineering community. And I hope in this talk today, we can convince you a little bit about why that's important, how testing has a role to play, and in particular, how this is relevant for deep test, because the kinds of simulation we're building today are not like those that were built back in the 80s and 90s where simulation started. Particularly when we start to build simulations of social media, we need to simulate users, and that requires all sorts of imitation learning, as we'll see. And in particular, from a testing perspective, it raises the most pernicious version of the Oracle problem. If you like, simulation is the worst possible case for the Oracle problem. Not only do we not know what the correct output should be for a given input, but it's inherently unknowable. We're building a simulation after all, and we're simulating possibly counterfactual behaviors in circumstances we've never actually seen before in reality, and therefore the Oracle is unknowable. So you may think, well, how can we test? And in this talk, we're going to show you how. So I just want to spend 10 or 15 minutes here a little bit about the dub cyber digital twin we've built at Facebook to set the context for Natalia's part of the talk, where she's going to be telling you in much more detail how we do metamorphic testing. So the Facebook infrastructure you can think of at a top level abstraction consists of databases and processing elements. And on top of that infrastructure, we deploy bots. And these bots simulate normal user behaviors, but the actions that they perform and the observations they make from the infrastructure use exactly the same call stack as you use when you make actions and observations on the Facebook platform. So unlike traditional simulation where you simulate the artifact, the engineering artifact, like Boeing might simulate an engine, in our dub simulation, what we're doing is we're using the real infrastructure, and it's only the users that we need to simulate their behaviors. And so when a bot sends a message to another bot through our cyber digital twin, that bot goes through the same back-end call stack as you would if you send a message to one of your friends on Facebook. So that's it's hundreds of millions of lines of code, in fact, that are essentially being brought to bear in this simulation. And we've got this layer on top of these bots. So what do? Well, we record the bot. We reward the bots for being bad to other bots. All the interactions between bots are, of course, isolated, so they only occur between other bots. So we reward bots for being bad to each other through the infrastructure, but they can't interact with normal users. And we train the bots using a variety of techniques, including machine learning. The simplest technique is not machine learning based. We just use rule-based behavior. It's very useful for capturing extreme kinds of behavior where we want to specifically capture, given good old-fashioned AI, rule-based approach. So the rule-based approach we've used so far has involved a depth-first search, so that the bot crawls in a depth-first manner, choosing friends according to these depth-first rules. And when no friends are available, the bot backtracks. And so it's essentially simulating what a new user on the platform might do as they navigate around. But we also use supervised machine learning techniques, in particular imitation learning techniques, where we take existing data. So we collect anonymized data, we learn generalized patterns from that, and then we use that to train our bots to imitate reality. So this is a kind of imitation learning. It's non-counterfactual in the sense that we're imitating what we've seen before happen on our platform. But we also use unsupervised techniques. We've experimented, for example, with using reward criteria and then having the environment issue rewards and using this as a way to train bots using reinforcement learning. So we have a whole collection of different tools for training bots to essentially simulate real user behavior. And there's an overview position paper presented last year at ICSI on this called WES, Web-Enabled Simulation. And we have an update on this paper coming out shortly at the EASE conference. There'll be a keynote later on this month, in fact, on that topic. So I'd like to just illustrate a little bit of the kinds of things we can do with this dub platform. So we go after harmful behavior because we want to try and design our products to make it harder to achieve these harmful behaviors, while at the same time not inhibiting the ability to do normal behavior. And in particular, We want to try and migrate from a posture of detecting harmful behavior and trying to stop it to a policy of being able to prevent harmful behavior by baking into the design of the systems the friction that makes it much harder to achieve harmful behaviors on the platform. So I want to illustrate how this works with an analogy with driving. Imagine it's a lovely sunny day, you're driving along a lovely street in a camper van, enjoying the joys of summer, lovely day, birds are singing, and it's nearly knocked off the road as a car speeds past you, going way past the speed limit. What can you do about this? Well, as the driver of the camper van or one of the passengers, there's very little you can do apart from cursing and maybe choosing a different route. But as the owner of the infrastructure, the provider of the road, there's quite a lot you can do. And in fact, we design our roads. There's a mechanism that we design in order to try and prevent speeding. In the UK, a speeding camera looks like this. It's a yellow box and it takes photos when people do speed, and that's a detection technology. Contrast that with a prevention technology. We have speed humps. Many countries use this. You put bumps in the road, it makes it harder to speed. Interestingly, in the UK, notice those detection cameras are painted bright yellow. That's because they're trying to turn a detection technology into a prevention technology, because it's much better to prevent speeding than it is to just detect it after it's happened. The trouble with prevention with a physical engineering material like a road is that you put these speed humps in, they don't actually stop someone speeding. They make it even more dangerous when they do, and they hurt the normal users who are trying to just drive normally because it wrecks the suspension in their cars. Nevertheless, despite all those challenges, it's still a technology we use, and those limitations are limitations that are there because it's a physical engineering material. Think about how we could do mechanism design with a software material. Suppose we have these bots that we're rewarding for crawling the platform. Maybe they're doing scamming type behavior to find people to scam. They're doing these actions and observations. Now we impose the software equivalent of a speed hump. Maybe it's a kind of a rate limit to limit the number of a certain operation that a bot can achieve. So now what we're doing is we're essentially building a constraint vector that lies in between the bots and the platform infrastructure. And this constraint vector can be different for each bot. For example, for the first bot, we might say, well, you can only send 4 messages per minute. You can only read 12 per minute, and maybe you can only join 17 groups in total. These aren't constraints we'd apply to a real user, but they're constraints we can experiment with on that particular bot. And then this bot has different values. And the third bot maybe has some values which it shares with the second bot and some values it shares with the first bot. So those who are familiar with the ideas of evolutionary search will see here that what we're really doing is we're defining a kind of a search space. This constraint vector is a search space where it's obviously much larger than 3 constraints per bot. There are many, many different parameters we could tweak to constrain how the bots behave. And what we're really doing is we're searching for that little sweet spot, maybe a few small tweaks to these parameters that will simultaneously make it much harder to achieve the bad goal, the bad behavior, while not at all inhibiting the good behavior. Now, whereas with a road, when you build speed humps, it's a physical engineering material and it wrecks cars. With software, there's no reason why we have to be purely agnostic about what our software is for. We can potentially try and search for these small tweaks that essentially solve a bi-objective optimization problem. On the one hand, you have the fitness that says it must be harder to do bad things that the platform's not really designed for, but at the same time, as easy or even easier to do the good things. So this is a classic bi-objective search-based software engineering problem. The search space is very large, and you might think, well, this is like looking for a needle in a haystack, and it is indeed a hard search problem. But in the software engineering community, we have exactly developed over the last 20 years technologies which are designed specifically to tackle this problem. So essentially, search-based software engineering is all about taking these problems formulated as search in this way, thinking of these rate limits as part of a search space, and then trying to search the space using the reward of the bots to guide them to try and break the criteria, and then using that to measure fitness for how effective they are at achieving bad behavior and how effective normal users are at getting their behavior done. So this is how we think of mechanism design in our Facebook. Now, we just a few days ago at ICSI, at the main conference, launched a funding call for funding in the area of social media simulation. The deadline is July the 7th, 2021. And I really would like to encourage you to take a look at the call for funding proposals in this area, because we've tried to make it very friendly to software engineers. So the first thing that makes it friendly is you only have to write a 2-page proposal. So it's unlike those who've got experience with, say, the European Union funding proposal systems or the Department of Defense in the United States. We've tried to make it very, very light touch. You write literally a 2-page proposal, so it should be, you know, an afternoon or at most a day's work to put together a proposal. And then we'll fund up to 5 of these, and the amount we'll fund them for is up to $100,000 per proposal, which is double the amount we offered last year. And this is part of an overall program of offering funding in requests for proposals that we launch once per year. As I say, we launched one last year at ICSI. It was 5 proposals of up to 50K then. Now it's 5 of up to 100K. And next year, we hope if this call is successful, we'll be scaling up once again and looking to build really close relationships and collaborations with our colleagues in the scientific community and in academic institutions to work with us on this problem of building social media simulation and being able to test and verify the results. Essentially exactly what the Deep Test workshop is all about. The other thing that makes it attractive this year and last year is that it's an unconstrained gift. So if you're one of our successful applicants, then we'll give you the funding, and essentially it's an unconstrained gift. We make absolutely no constraints on how you spend that money to support your research. So having been a professor for several decades before coming to Facebook as a research scientist, I know how valuable it is in a lab to have funding that is unconstrained in that way. You can spend it on absolutely anything to support your research. We don't make any windows into how you spend your money, as long as it's going to help your research, of course. Your university or educational institution may place some constraints, but essentially on this funding, you'll have the weakest constraints that apply. You'll have the easiest process to apply. As I say, just 2-page proposals, and the deadline is the 7th of July. Happy to take questions about the funding call as well as the work we've been doing at Facebook. The call itself, there is a web presence about this, which I can point you to in the chat afterwards. And just to give you the TLDR on this, there are 3 key topics we're looking for. We're looking for work that will help us with testing and verification of social media simulation systems, work that will help us with scalability, essentially balancing that classic engineering trade-off between the fidelity of the simulation and the speed with which you can get the results. And finally, the problem of modeling human behavior, modeling with sufficient value to give actionable conclusions. So essentially, at least 2 of those topics are directly relevant to Deep Test. There's the modeling and machine learning aspects, and there's the testing and verification aspects. So I hope that everybody at the workshop will find this call at least interesting and will want to consider applying. So essentially what I've covered so far is how we build this cyber digital twin of Facebook that allows us to explore these search spaces of possible rate limits that we can apply to make it harder for our bots in the simulation to achieve bad things on the platform while not hurting normal users. What I'd like to do now is to hand over to Natalia, who's going to tell you, how do we go about testing something like this, given the problem of flakiness and the problems of the oracle and all these problems that we know, which I'm sure are well known to people in the Deep Test community. So thank you very much for listening to my part of the talk. It's now my great pleasure to hand over to my colleague on the team, Natalia Guksevska, who's leading our engineering effort on testing web-enabled simulation at Facebook. Thanks very much. Over to you, Natalia.
Thank you, Mark. I'll just share my screen. Okay, so in this part of the talk, I'm going to give a little bit more details about how are we testing the implementation of web-enabled simulations at Facebook and the underlying challenges. So as Mark mentioned, One of the things that makes simulation hard to test is we don't know what the result of a simulation should be. If we know, we wouldn't need it. So that makes it by default very hard to test. And the second thing is we use down the line that we use for simulations is the real Facebook infrastructure. There are constant changes landing in that code base daily by thousands of engineers. And also the data on which we're operating is modified daily by billions of users. So that makes it hard to test, as we're going to see later. So what do we do to overcome these challenges, or at least write some tests to test the simulation that Mark just described? So the first thing to think about is, well, it is just software. We can write a formal mathematical specification, and we can compute what the output should be, and we can just test it. But as we know, the code base is huge. By the time we have a mathematical specification, probably the code will change thousands of times and we'll need to write another one. The second thing is we can use another model as a reference, but again, we have the same problem. Another thing is we can use an implicit oracle, and we actually do that for end-to-end testing. For example, if the simulation crashes, we're sure that that is not the expected outcome. We could use another system as a reference, but then we have the same problem. How do we test the system that we use as a reference? And the last thing is, what if we use exactly the same system as a reference? And that is what we actually do to test the web-enabled simulations at Facebook through metamorphic testing. Before I jump in the testing that we're doing, I would like to give a simple overview of what a metamorphic test looks like. So let's say we have the sign transformation, and we know that for two different inputs, there are certain relationships that should hold true. Testing that these relationships hold true, like a sign of x and sign of 2p plus x, is basically metamorphic testing. There was a survey published in 2016 that provides a comprehensive survey on metamorphic testing. So it summarizes the research results and the application areas of metamorphic testing. And it is very interesting to see that over time, the interest and the publication on metamorphic testing increase. And since 2005, that trend of research programs used in the published articles and real-world programs used in the published articles seem to be following the same growth trend. That being said, we are very happy to share that our team has the first metamorphic testing framework deployed in continuous integration in industry. And we actually are very happy to say that we published a paper in the at ICSI, at the SEIP track on the metamorphic testing that we are doing for the web-enabled simulations. In the next part of this presentation, I'm going to go in a little bit more details about the setting of the simulation that we have in this paper, and also the different metamorphic relations that we have to test the simulation. So first, the setting of the simulation. As Mark described, we have a simulation can simply be a bot traversing the social graph. So to explain what traversing the social graph means, like if a bot knows of the existence of one specific person, they can go and visit their profile, leaving the simulation in a specific state S1. They can look at their friends and decide who is the next person to visit. Look at their friends, choose the next person to visit, and so on, and all that specified by persona. So bots have personas. Personas encapture the demographic of the bot and the behavior that this bot is presenting. So basically, let's not think about how do we train the bot behavior, but just what can they actually do. So if you talk about a bot that is harmless, they would be visiting the social graph without a specific intent. They just want to see what people are doing on the platform. But if we talk about a harmless bot, they are visiting the social graph with some intent. So they are not considering all the next people, all of the person's friends to visit next. They are only considering the people that are likely to respond to what are they looking to achieve by visiting their profile. So that is the difference between harmless and harmful bot behavior. The third thing is Mark talked about mechanism design. So in the paper in particular, we talk about rate limiting, about what the platform allows users to see when crawling the platform. In particular, how many friends the bot can see when visiting someone's profile. And let's say we have a bot visiting a person with 5 different friends. If the rate limit is set to 1, the platform is going to show at most one friend to visit next. So the bot, independent of their behavior, doesn't have a lot of choice. They just know about the person they visited previously, and they know about the one more friend that is left that the platform is allowing them to see, and so on. So that is about rate limits. And the last thing is the different simulation modes. I'm going to go in more details later. Why do we need the simulation modes? But the important thing to know is that in online simulation mode, the bot is interacting on the real social graph, the social graph that many users are interacting on daily. So basically, we need to know that for that social graph can change at any time between 2 different simulations or during exactly the same simulations, like we can see in this graph. There is user number 3 that deletes their account, and user number 5 and 4 become friends while the bot is crawling through the social graph. So during one specific simulation. And then there is offline mode. In this case, the social graph is not going to change during the simulation or between 2 different simulations, because the graph is snapshot of the social graph at a specific point in time. And we use exactly this mode to reduce flakiness, as we're going to see in the next slides. So first thing, why do we have test flakiness? Well, as I showed, the social graph can change at any time. First thing, we don't know what the result can be, but if we compare 2 different runs, if the graph changed between the 2 different runs, it is hard to say that the result should remain the same, because the graph is not the same anymore. There is infrastructure non-determinism. I think we have all seen, we have all opened the page that doesn't load, and after 2 seconds, the page loads because of X reasons. That can happen during simulation as well. And the simulation is not going to see that it is just transient infrastructure error. The last thing is simulation sampling. So there is a lot, even in rule-based simulation, there is a lot of randomness. And if we are not careful, how do we use that randomness? We can, 2 simulations with exactly the same input can lead us having 2 different results. So that can introduce test flakiness as well. So what are the metamorphic relations we test in MIA? Well, one type of metamorphic relations is based on bot behavior. So as I mentioned before, when the bot traverses the social graph in 2 different runs in online mode, let's say the runs even start at exactly the same time, we would expect the output of the simulation to be the same, because the code is same, the input is same, the bot behavior is the same, everything is the same. But since the code can change in between, in reality, the output is not going to be the same. The 2 bots are going to probably visit different parts of the social graph. So this is the identity relationship. We would like the outcome of such simulations to be exactly the same. And that is why we can run these simulations in offline mode on a snapshot of the graph and actually verify if the simulation is performing correctly by comparing the outputs of the simulation run in offline mode. The second type of metamorphic relations that we test is based on bot behavior combined with rate limits. So let's say we have two bots that are supposed to behave differently, running in offline mode. If we don't have the rate limit in this case, we would expect them these two simulations to give two completely different results. But if we set a very restrictive rate limit, such as at every step, each of the bots have exactly the same choice. Like they don't have two friends to choose from. They have they have at most one friend if the person that they're visiting has friends, of course. In this case, with a very restrictive rate limit, we can define actually a metamorphic relation that tests that the results of these two simulations are exactly the same. And that is thanks to the restrictive rate limit. The third type of metamorphic relations that we test is based on different bot personas. So the bots that are crawling through the social graph can belong to a different age group. So these bots do not represent a specific person, but they capture the behaviors of people in their 20s and in their 50s. And if these two types of persona traverse, even in online mode, the social graph, there is specific type of people that we are expecting them to visit. We are expecting them to visit people that are very similar to them in very similar age group. So that leads us to defining metamorphic relation between these two different simulations based on the different personas, such that the average age of the people visited by bot in their 20s is smaller than the average age of the people that a bot in their 50s visited. So these are not the only relationships that we test that we present in the paper. So there is this figure in the paper summarizing the different relations and the different bot behaviors for each relation that we use in order to test the simulation. And one interesting thing to observe is that we have managed to reduce flakiness that is very frequent in online mode by running the simulation in offline mode. On top of the metamorphic relations that I just mentioned, I would like to say that in the paper we talk a little bit more about end-to-end testing, and in particular using an implicit oracle, which means if the simulation has crashed, then we know that the simulation has failed. And I'm going to mention later on how are we extending this part. And we also showed that regression testing is a specific subtype of metamorphic testing, where the simulation is run on two different versions of the underlying code. As I mentioned at the beginning, the testing framework that we implemented to test the simulation is part of continuous integration system. This means we have bots commenting on changes that people submit for review. Bots comment on developers' pull requests to give them a signal whether the changes that they have implemented are breaking the simulation or not. And beyond the paper, after publishing this paper, we continued extending our testing framework with diff sniffing. I know this does not mean a lot outside of Facebook, so I'll need to say a little bit more about it. So diff sniffing is basically commenting on changes that developers submit that are not directly changes to the simulation. So Mark at the beginning mentioned that we are modifying that we are running the simulation on the underlying infrastructure. So the simulation is supposed to warn us if there are problems in the changes that we implement in the underlying infrastructure. And deep sniffing is meant to give that signal when modifying the underlying code. And the second thing is we're extending end-to-end testing beyond only the simulation crashing. We're running a simulation. We know that there are certain things that for sure should happen during the simulation. And we are now introducing properties in order to make sure that these things hold true during the simulation. With that being said, thank you for your attention. I think we can now, we're now open for questions.
Thank you both for your presentation. Now we have 24 minutes to answer your questions. The first question from Sergio Segura that is complimenting you for the great talk. Have you considered using metamorphic relations for detecting performance bugs, assuming that performance is an issue? We proposed also a trivial one. Increasing the number of bots should increase simulation time, assuming the same configuration settings. So have you considered performance bugs?
I'll start and then I'll hand over to you, Natalia, if you've got anything you want to say. So yes, as Natalia said, we characterize regression testing as a special case of metamorphic testing. So in the paper, there's some details about this. It's a relatively simple piece of theory to show that you can recast regression testing as metamorphic testing. And therefore, that means we've implemented regression testing in the MIA system just as a special case. And what that means is that we also can check whether we have a performance regression, which is the thing that really worries us. So like, as Natalia was saying, we have this offline mode. It has benefits for testing, but its main benefit is that it actually speeds up the simulation by orders of magnitude. And so we do care a lot about the performance, and we have the ability in our regression test to detect performance regressions. I think we actually, so I recall an earlier version, we actually had a test for that, but I'm not sure it's in the current version. So it's not something we've gone after massively aggressively at this point, but it's definitely something that we can do within our framework and have thought about doing. And I think did play with it at one point, if I recall.
So does Natalia have to add anything? We will be really curious about the details.
I think Mark covered everything, but I definitely think we could use, if performance is challenged, something that we need to consider in the future. I think metamorphic testing can help test that aspect as well. Yeah.
So
I think some of the I was just sorry, just go ahead, Vincenzo. Sorry,
please go ahead. Go ahead.
Oh, I was just going to say, Natalia was also talking about properties, and while we played a little bit with regression testing for performance, I think if we can, there's no reason why performance can't be a first-class property as well. And other things like memory consumption. You know, another big concern of ours is to make sure that these simulations can run in the kind of elastic cloud infrastructure that we have at Facebook, and that has some tight memory constraints. So, yeah, we do some testing of these non-functional properties in a separate way, but I think we can start to imagine bringing them in as properties in future. I see you're nodding, so I guess you agree, Natalia, but I don't know. Don't put words in your mouth.
But what is the effect of using many bots together?
So I think the configuration of using exactly one bot in this presentation is for simplification reasons. But using multiple bots at the same time is going to affect the performance of the simulation if we introduce thousands and thousands of bots. But it depends on the size. If we are looking at smaller simulation, we have the ability today to run multiple bots at the same time and summarize the results from them. Do you want to add something, Mark?
I think you've covered that very well. Thank you.
Okay, let's go to the next question from Ginelle. She also compliments for the great talk. I agree. She asks, how is the behavior of the bot classified into not harmful, harmful, or pretty harmful? Yes, Mark goes first, and then Natalia. Let's keep the same order.
Oh, well, actually, exactly as you intimate there, Gunnar. So we distill out, using imitation learning, we distill out harmful behaviors so that we have a kind of a, you could imagine a super harmful like version of a bot that actually only does harmful things on the platform. Obviously only to other bots, I should stress, right? And then we have every gradation in between, and that becomes another kind of a persona, like what Natalia was talking about, these personas. So the degree of harmful intent can be dialed up or down, and when we can see the response in response to that.
Natalia?
I think teammates that are not currently in presentation would answer this question much better, but I will try to add something to what Mark said. So about harmful and pretty harmful behavior, you can distinct these two types of behavior of why did the user create the account. There are people that there can be a bot that uses one part of the time the platform as a normal bot, and another time of the platform as a pretty harmful bot. And their intent is not only the harmful behavior. So we can mix the two types of behavior to create bots that are a little bit harder to stop from what they're doing on the platform, or for introducing harm on the platform.
Pretty philosophical question that it could be deeply silly, but I'll go it anyway. Are the bots that are not totally harmful in their behavior more harmful because they are able to win the user's trust?
That depends very much on the context and the particular kinds of harmful behavior. You'll appreciate that for all sorts of reasons of not just commercial sensitivity, but not wanting to put into the public domain some of the techniques that we use to tackle harmful behaviors, that means that Natalia and I can't talk in specific details about the kinds of harmful behavior. I mean, we all know what kind of harmful things can happen online, and we're trying to tackle all of them using this approach. But it's probably best that we don't get too much into the detail of the very specifics of what kind of mechanisms we use, because on the one hand, it's not really, it doesn't affect the scientific aspects of the work, you know, like the metamorphic relations and so on. You can understand those without that. But also, there's a slight risk that we might actually, you know, help those who want to achieve harmful aims, and we'd rather avoid that if that's okay.
Yeah, I agree. So let's go to the next questions. That, yeah, from the perspective of the testers, what should we consider as a test? Asks Andrea. Is it the digital twin model?
So I assume it's the question who was, and
okay.
I would say, so there are two different ways to look at the metamorphic test that we just presented. We started by testing the simulation. So basically, we're testing when changes are introduced directly to the simulation, we test whether the behavior is still the behavior that we would expect, or the changes have broke something. But now with deep sniffing, the extension that we are implementing, we are also looking to test beyond the simulation, like even if the simulation does not change, but the underlying infrastructure has changed, we're still going to run the simulation and see whether, and basically the tests, exactly the same tests that were supposed to test initially the simulation, are going to test whether the changes broke the underlying simulation. Mark, do you want to add something?
Yeah, I think it's a very good question, this, who tests the tests? You know, it's a standard testing question. Facebook, we have this principle, which a lot of the tech companies have, of dog fooding. You know, so it wouldn't be right to put up a testing infrastructure and then not have it test itself. And so, in fact, Mia has a concept for each use case of a golden set, you know, a golden set of test problems. And there is one for self-testing as well. So it can retrieve this this golden set and then test on itself. So in fact, you know, Mia really is a golden retriever that eats its own dog food.
And can the test be healed by your twin model? So if tests that are failing or are flaky can be healed by your approach.
So I didn't quite catch the question there.
If you have tests that are flaky or are failing, do you also have mechanisms, any mechanism to heal them, so to make them work, to repair the test?
We don't apply repair to the tests, but as Natalia mentioned in her part of the talk, the offline mode does essentially make a lot of tests that would be highly flaky due to changes in the underlying social graph and non-determinism inherent in the platform makes those problems go away. And that helps a lot with flakiness, as Natalia mentioned. Natalia, did you want to add anything?
No, I just wanted to say that we have it as an open challenge in the paper, actually. It would be eventually great to be able to detect errors and then fix them automatically. But at the moment, that is still a research point.
And have you found the common reasons for the test to fail? A specific kind of flakiness, as an example.
Test runs in online mode, meaning running on the same social graph as that real users do. We have seen a lot of tests being flaky. That is the main reason I would say that we see as a common flakiness among the tests.
There is the next question from Alberto. He asks about the personas. So you mentioned the personas being in their 20s and their 50s. Could it happen that the average visiting age of the 20s group is greater than the 50s, and still that the behavior is correct, in the sense that there is always some non-determinism? How you handle non-determinism? Is it always reported as a bug or as a warning?
This is a great question, actually. It can happen. Absolutely. What we do now is when testing these types of relationships, we have multiple runs of the persona in their 20s and persona in their 50s. And we do take the average over multiple runs. We don't use only one run to test this metamorphic relation. And initially, also going back to the question, what tests the test? Initially, all the errors that were reported with this testing framework were warnings, so that developers can share whether the failing test makes sense or it doesn't. And it also helped us improve the test and reduce noise during change time.
Mark, do you want to add something about the personas?
No, I think Natalia's covered it. I mean, I've witnessed the persona difference myself, because I was on that slide, that Natalia put up there. I mean, I have a different persona to most of the other Facebookers, not just because I'm an academic, but I'm in a different age demographic for a start. So it's a fascinating problem, and I'd love to see more research on this area.
That's right, I agree. There is another question from Andrea that it talks about the difference between the offline and online faults. Are the offline faults representative of the online ones, or only of a subset of them? And what about unseen conditions that cannot be simulating during offline mode? How do you handle them? You just ignore it?
Indeed, the faults detected in offline mode are clearly only a subset of what we can detect in online mode. And that is the main reason why offline mode is not the perfect solution to the test flakiness. If we can avoid the flakiness in online mode, that would be much better.
I see Mark nodding.
Yeah, thanks. It's a very astute question, and it's correct. Yes, you don't get anything for free in computer science, right? So everything's. I often was guided by a colleague of mine who said that in life you don't get to choose to have no problems. You get to choose which set of problems you want to live with and which set of problems you want to avoid. And offline mode allows us to avoid flakiness and give us a strong signal, and it's fast. But as Natalia says, that means that we are testing a subset of behaviors, and therefore our coverage has gone down of problem space. However, there are some online tests which aren't flaky. It's not as if they're inherently like everything's a disaster. So the persona-based test that Natalia talked about is run online and is essentially asking a statistical property. And so statistical properties are inherently more robust in the presence of flakiness. And I think there's a lot of very exciting research to be done that kind of assumes that we're in a world where tests are flaky, and that tries to actually cope with that rather than just sort of shut our eyes and so offline mode is our way of tackling flakiness to give us fast, quick signal, but it's not the whole picture. We use statistical metamorphic relations like the one that Natalia presented to tackle more online challenges, and scaling those, of course, is a challenge, because as soon as it gets statistical, you've got to run multiple simulations and so on. So would love to see research on how to live in a world where tests are flaky and test signal is a statistical property, and that is very well fitted to machine learning, to deep testing, and to testing simulation-based systems.
Yeah, I guess that also the following question from Andrea is about this and about the stochasticity to be avoided at all costs, or it can be leveraged. Yeah, I guess that it's covered by your answer. That was a perfect answer.
Yes, I think that's I didn't read that. I promise I didn't read that before giving the answer, but I have just read it now, and I agree wholeheartedly. Yes, we need researchers. If you look at the research literature on flakiness, it tends to either say, let's have a technique for detecting it, or let's try and avoid it. And there should be a third way, which says, let's live with it, and let's actually even maybe exploit it so that it's part of our signal. And we have to reformulate a lot of our ideas about testing in order to do that. So that's a very exciting open problem for the research community, that we can throw out some of the real world kind of relevance and impact of that work, but we can't solve all of those fundamental scientific questions all ourselves in industry. We really need help from academia on that.
Well, you talked about modeling human behavior, but humans can also be flaky. They can answer in different ways to the same input, depending on factors that you can hardly control.
Shall I take this from Natalia? Do you want to? So yes, in fact, in the paper we talk about three sources of non-determinism. There's the social graph changes under your feet. So while your boss is traversing the graph, someone just changes their friend list, and then boom, everything's different, right? That's dealt with by offline. There's the infrastructure, which is inherently built to not care about certain things. So you issue a query, and the query is a search result, and the search result is inherently going to change, or it might be optimized in different ways. That is also dealt with by offline mode. Then the third is the user themselves. Different users are going to react in different ways, and depending on their mood and so on. And this is what we try to capture with personas. So, you know, you could imagine that one persona might be a very flaky persona, and another is a very sort of, you know, people come in personality types, right? So, you know, I think this is why the whole area of personas is area to research, and combining that with the problem of verification and validation gives you another very rich seam of research questions. You know, if you imagine a simulation of user behavior, it's not necessarily social media, any users, and you want to capture their personas, and then you want to make tests that are going to reveal corner cases that particular kinds of user behavior would expose. That's a very interesting research problem.
Yes, I agree. Also, the people from IoT try to model human behaviors to prevent dangerous things from happening. And there is another question from Gunel. She asks, are there examples of preventive actions Facebook has added to its real system based on the results of obtaining using the digital twin? So what is the impact of your research to the product and the services from Facebook?
So just before I answer this, and I'll hand over to Natalia as well afterwards, but just want to remind you, we can't talk too much about the specifics of things we've deployed, you know, because that obviously could, especially when we're talking about harmful behaviors. In terms of the impact, we have actually mechanisms that we've discovered in production. We've experimented with those. And the other thing is that this approach that Natalia has been talking about essentially using the simulations as another kind of testing at the social level is actually currently deployed, and we're planning to scale that out much more. So I can talk about that in the general sense, but I can't give specific examples. I hope you'll understand for obvious reasons. Yeah.
Natalia. I won't force you to talk about the details you cannot reveal. Be careful.
I think Mark covered everything.
Okay, so there is hope for us academics. We can have impact on real products. That's great.
Oh, good heavens, yes.
This is very good. We have 3 minutes and 3 questions. I don't know if we can make it, but at the end of this session in 2 minutes, it will start. There will start a sequence of 2 videos, but you can still chat with Natalia in the opening room. So the last question is from Simos. I'll choose Simos because it's the shortest. Excellent talk. Thanks both. Were there instances in which both personas were not meaningful at all, did not provide useful results, or led to incorrect insights? Or is it the other way around?
I think we have a bigger problem with false negatives than false positives in general. You know, it's such a big space. Almost anything, with 2.7 billion users, almost anything the bots can do, real users probably will do at some point.
Natalia.
I'm going to say something similar. As Mark, I think it is hard to simulate something that wouldn't be meaningful. Like, since we're using the real infrastructure, anything the bot can do, like real users can do them as well, and they would probably do them. So it is hard to simulate something that wouldn't happen on the platform.
Probably I did not catch it from the presentation. I'm sorry for that. But do the bot communicate between themselves? So it's like someone can fetch information and the other can exploit them.
They can definitely do communicate between each other. Yeah, in the presentation, I did not mention that because we were looking in the scenario of having exactly one bot. But if there are multiple, bots can communicate between themselves. They just cannot talk to the real users.
Mark?
As Natalia said.
Okay. So I guess we cannot answer in 30 seconds both the question from Michael and Sergio. You can answer in the chat, or you can open a private chat between the two of you. But I want to remind everyone that is attending to check the link that Mark has shared, because it's a great opportunity for us academics to do research in industry. And so we will start now with the presentations.